Hello Chem 1A, this is Chapter 6, Lecture Video 10, and this is our last lecture video for the chapter, and we're covering our last topic in this lecture video, which is bomb calorimetry, which is a fancy name for something known as constant volume calorimetry. Bomb calorimetry is often the common name for it, and constant volume calorimetry, as its name implies, is where we're measuring the transfer of heat while maintaining a constant volume. Now, generally, bomb calorimetry is used for combustion reactions, usually to determine either our internal energy or our delta U, right? Delta U or delta E, they're the same thing. So we're really just trying to determine internal energy, right? Now, how does it work? Well, if we look over here at this diagram, it's not nearly as crazy fun as it sounds. When I first did bomb calorimetry, I was a little disappointed. You don't even hear an explosion, which was sad for me. But what we do is we take this container here at the bottom. You kind of have the cutout view of it, and it's removable. And you put whatever substance you want to explode inside of it, and you attach ignition wires to it. So that's what these orange wires are leading in. And those orange wires will eventually explode the substance when we run an electric current through it. It ignites it. What we also do is we pack this container filled with O2 gas, which is flammable, right? And when that ignition wire goes through, the substance will react with the oxygen to form carbon dioxide and water, just like pretty much every combustion reaction does. And we can measure how much heat occurs because what we do is we fill the rest of the container up, this blue space, with water. And we make sure we know the initial temperature of the water and the bomb. And as the explosion heats up the bomb, right? So as the explosion happens, we have energy coming out of the system and into the bomb calorimeter. Now this bomb then heats up the water around it, which we can measure. At the end of the day, we can kind of use two reactions to calculate this process. Now we can use Q of the reaction plus Q of bomb has to add up to 0 because whatever the reaction gives off energy-wise is going to be exactly what the bomb gains. Then Q of bomb we can calculate using the specific heat capacity of the bomb, which is usually given, times delta T. So it's kind of in a modified Q is equal to MC delta T here. Q of the reaction is generally what we're trying to solve for. So usually what we do is we use these values to solve for the Q of the bomb. Then we take the Q of the bomb, plug it in here, and solve for Q of my reaction. That's usually not where we stop though. Like delta H, we can calculate delta E or delta U using Q of the reaction over moles of the reaction that occurred. In this case, it's not the same thing as delta E because we have pressure changing in the process, which means we can't calculate delta H here because we're not under constant pressure conditions. Pressure is definitely changing inside that bomb calorimeter, and so any energy transfer we measure is not going to be defined as an enthalpy value, a delta H. So let's do an example problem. We're going to blow up 3.3 grams of glucose, and it's ignited, we burn it, we form H2O and CO2, and when this happens, the temperature changes from 22.4 degrees Celsius to 34.1 degrees Celsius. If the calorimeter has a heat capacity of 847 joules per Celsius, what is delta U slash delta E, right? They're the same symbol for internal energy per 1 mole of glucose. All right, so in this case, delta E slash delta U is going to be equal to Q of the reaction divided by moles of glucose because we're in per mole of glucose. So the first step here is to use our values to calculate Q of bomb. We know Q of the bomb is equal to C of the bomb times delta T. And that is equal to 847 joules degrees Celsius times our delta T, which is 34.1 degrees Celsius minus 22.4 degrees Celsius. This gives me a value of 9,909.9 joules of energy. Next, we use our equation Q of our bomb plus Q of our reaction equals 0. And we know Q of bomb now. So, right, Q of reaction effectively simplifies to negative Q bomb. Or in other words, Q of my reaction is equal to negative 9,909.9 joules. A lot of nines. Next, we need to get moles of glucose. Well, we can do that pretty easily. We have 3.3 grams of glucose, which is C6H12O6, and we can use the molar mass to get moles. Now, calculating that molar mass, we get 180.18 grams of C6H12O6 per 1 mole of C6H12O6. And this will get us 0.01832 moles. So delta E then is simply equal to negative 9,909.9 joules divided by 0.01832 moles. This gives me negative 541,000, give or take, joules per mole. Since I didn't specify what units of joules, this would be a totally acceptable value. I would probably give it in kilojoules personally, negative 541 kilojoules per mole is more accurate, and technically it should be only 2 sig figs, so negative 540 kilojoules per mole. All right, and that's pretty much it with bomb calorimetry. If you have any questions, please let me know. See you in office hours.